Biography of world top scientist Galileo Galilei. Galileo Galilei, the 15th of February 1564 to the 8th of January 1642, was an Italian astronomer, physicist, engineer, philosopher, and mathematician who played a major role in the scientific revolution of the 17th century. He has been called the father of observational astronomy, the father of modern physics, the father of scientific method, and the father of science. His contributions to observational astronomy include the telescopic confirmation of the phases of Venus, the discovery of the 4 largest satellites of Jupiter, named the Galilean moons in his honor, and the observation and analysis of sunspots. Galileo also worked in applied science and technology, inventing an improved military compass and other instruments. Galileo's championing of heliocentrism and Copernicanism was controversial during his lifetime, when most subscribed to either geocentrism or the Tychonic system. He met with opposition from astronomers, who doubted heliocentrism because of the absence of an observed stellar parallax. The matter was investigated by the Roman Inquisition in 1615, which concluded that heliocentrism was foolish and absurd in philosophy, and formally heretical since it explicitly contradicts in many places the sense of Holy Scripture. Galileo later defended his views in dialogue concerning the 2 chief world systems, which appeared to attack Pope Urban VIII and thus alienated him and the Jesuits, who had both supported Galileo up until this point. He was tried by the Inquisition, found vehemently suspect of heresy, and forced to recant. He spent the rest of his life under house arrest. While under house arrest, he wrote one of his best-known works, 2 New Sciences, in which he summarized work he had done some 40 years earlier on the 2 sciences now called kinematics and strength of materials. Early life and family. Galileo was born in Pisa, then part of the Duchy of Florence, Italy, on the 15th of February 1564, the first of 6 children of Vincenzo Galilei, a famous lutenist, composer, and music theorist, and Julia, who had married in 1562. Galileo became an accomplished lutenist himself and would have learned early from his father a skepticism for established authority, the value of well-measured or quantified experimentation, an appreciation for a periodic or musical measure of time or rhythm, as well as the results expected from a combination of mathematics and experiment. 3 of Galileo's 5 siblings survived infancy. The youngest, Michelangelo, or Michelagnolo, also became a noted lutenist and composer, although he contributed to financial burdens during Galileo's young adulthood. Michelangelo was unable to contribute his fair share of their father's promised dowries to their brothers-in-law, who would later attempt to seek legal remedies for payments due. Michelangelo would also occasionally have to borrow funds from Galileo to support his musical endeavors and excursions. These financial burdens may have contributed to Galileo's early fire to develop inventions that would bring him additional income. When Galileo Galilei was 8, his family moved to Florence, but he was left with Jacopo Borghini for 2 years. He then was educated in the Camaldolese monastery at Vallombrosa, 35 kilometers southeast of Florence. Name. The surname Galilei derives from the given name of an ancestor, Galileo Bonaiuti, a physician, university teacher and politician who lived in Florence from 1370 to 1450. His descendants had changed their family name from Bonaiuti to Galilei in his honor in the late 14th century. Galileo Bonaiuti was buried in the same church, the Basilica of Santa Croce in Florence, where about 200 years later his more famous descendant Galileo Galilei was also buried. It was common for mid-16th century Tuscan families to name the eldest son after the parent's surname, hence, Galileo Galilei was not necessarily named after his ancestor Galileo Bonaiuti. The Italian male given name, Galileo, and thence the surname, Galilei, derives from the Latin, Galileus, meaning, of Galilee, a biblically significant region in northern Israel. The biblical roots of Galileo's name and surname were to become the subject of a famous pun. In 1614, during the Galileo affair, one of Galileo's opponents, the Dominican priest Tommaso Caccini, delivered against Galileo a controversial and influential sermon. In it he made a point of quoting Acts 1:11, "Ye men of Galilee, why stand ye gazing up into heaven? Children, Despite being a genuinely pious Roman Catholic, Galileo fathered 3 children out of wedlock with Marina Gamba. They had 2 daughters, Virginia, born in 1600, and Livia, born in 1601, and a son, Vincenzo, born in 1606. Because of their illegitimate birth, their father considered the girls unmarriageable, if not posing problems of prohibitively expensive support or dowries, which would have been similar to Galileo's previous extensive financial problems with 2 of his sisters. Their only worthy alternative was the religious life. Both girls were accepted by the convent of San Mateo in Arcetri and remained there for the rest of their lives. Virginia took the name Maria Celeste upon entering the convent. She died on the 2nd of April 1634, and is buried with Galileo at the Basilica of Santa Croce, Florence. Livia took the name Sister Arcangela and was ill for most of her life. Vincenzo was later legitimized as the legal heir of Galileo and married Cecilia Boccainri. Career as a scientist. Although Galileo seriously considered the priesthood as a young man, at his father's urging he instead enrolled at the University of Pisa for a medical degree. In 1581, when he was studying medicine, he noticed a swinging chandelier, which air currents shifted about to swing in larger and smaller arcs. To him it seemed, by comparison with his heartbeat, that the chandelier took the same amount of time to swing back and forth, no matter how far it was swinging. When he returned home, he set up 2 pendulums of equal length and swung one with a large sweep and the other with a small sweep and found that they kept time together. It was not until the work of Christian Huygens, almost 100 years later, that the tautochrone nature of a swinging pendulum was used to create an accurate timepiece. Up to this point, Galileo had deliberately been kept away from mathematics, since a physician earned a higher income than a mathematician. However, after accidentally attending a lecture on geometry, he talked his reluctant father into letting him study mathematics and natural philosophy instead of medicine. He created a thermoscope, a forerunner of the thermometer, and in 1586 published a small book on the design of a hydrostatic balance he had invented, which first brought him to the attention of the scholarly world. Galileo also studied disegno, a term encompassing fine art, and in 1588 obtained the position of instructor in the Accademia dell'Arti del Disegno in Florence, teaching perspective and chiaroscuro. Being inspired by the artistic tradition of the city and the works of the Renaissance artists, Galileo acquired an aesthetic mentality. While a young teacher at the Accademia, he began a lifelong friendship with the Florentine painter Sigoli, who included Galileo's lunar observations in one of his paintings. In 1589, he was appointed to the chair of mathematics in Pisa. In 1591, his father died, and he was entrusted with the care of his younger brother Michelangelo. In 1592, he moved to the University of Padua where he taught geometry, mechanics, and astronomy until 1610. During this period, Galileo made significant discoveries in both pure fundamental science, for example, kinematics of motion and astronomy, as well as practical applied science, for example, strength of materials and pioneering the telescope. His multiple interests included the study of astrology, which at the time was a discipline tied to the studies of mathematics and astronomy. Galileo, Kepler and theories of tides. Cardinal Bellarmine had written in 1615 that the Copernican system could not be defended without a true physical demonstration that the sun does not circle the earth but the earth circles the sun. Galileo considered his theory of the tides to provide the required physical proof of the motion of the earth. This theory was so important to him that he originally intended to entitle his dialogue on the 2 chief world systems the Dialogue on the Ebb and Flow of the Sea. The reference to tides was removed from the title by order of the Inquisition. For Galileo, the tides were caused by the sloshing back and forth of water in the seas as a point on the Earth's surface sped up and slowed down because of the Earth's rotation on its axis and revolution around the Sun. He circulated his first account of the tides in 1616, addressed to Cardinal Orsini. His theory gave the first insight into the importance of the shapes of ocean basins in the size and timing of tides. He correctly accounted, for instance, for the negligible tides halfway along the Adriatic Sea compared to those at the ends. As a general account of the cause of tides, however, his theory was a failure. If this theory were correct, there would be only one high tide per day. Galileo and his contemporaries were aware of this inadequacy because there are two daily high tides at Venice instead of one, about 12 hours apart. Galileo dismissed this anomaly as the result of several secondary causes including the shape of the sea, its depth, and other factors. Against the assertion that Galileo was deceptive in making these arguments, Albert Einstein expressed the opinion that Galileo developed his fascinating arguments and accepted them uncritically out of a desire for physical proof of the motion of the Earth. Galileo dismissed the idea, held by his contemporary Johannes Kepler, that the moon caused the tides. Galileo also took no interest in Kepler's elliptical orbits of the planets, controversy over comets and the Asea. In 1619, Galileo became embroiled in a controversy with Father Orazio Grassi, professor of mathematics at the Jesuit Collegio Romano. It began as a dispute over the nature of comets, but by the time Galileo had published the Asea, Il Saggiatore, in 1623, his last salvo in the dispute, it had become a much wider controversy over the very nature of science itself. The title page of the book describes Galileo as philosopher and matematico primario of the Grand Duke of Tuscany. Because the Asea contains such a wealth of Galileo's ideas on how science should be practiced, it has been referred to as his scientific manifesto. Early in 1619, Father Grassi had anonymously published a pamphlet, An Astronomical Disputation on the Three Comets of the Year 1618, which discussed the nature of a comet that had appeared late in November of the previous year. Grassi concluded that the comet was a fiery body which had moved along a segment of a great circle at a constant distance from the Earth, and since it moved in the sky more slowly than the moon, it must be farther away than the moon. Grassi's arguments and conclusions were criticized in a subsequent article, Discourse on the Comets, published under the name of one of Galileo's disciples, a Florentine lawyer named Mario Guiducci, although it had been largely written by Galileo himself. Galileo and Guiducci offered no definitive theory of their own on the nature of comets, although they did present some tentative conjectures that are now known to be mistaken. In its opening passage, Galileo and Guiducci's discourse gratuitously insulted the Jesuit Christopher Scheiner, and various uncomplimentary remarks about the professors of the Collegio Romano were scattered throughout the work. The Jesuits were offended, and Grassi soon replied with a polemical tract of his own, The Astronomical and Philosophical Balance, under the pseudonym Lothario Cercio Sigensano, purporting to be one of his own pupils. The Asea was Galileo's devastating reply to The Astronomical Balance. It has been widely recognized as a masterpiece of polemical literature, in which Cerci's arguments are subjected to withering scorn. It was greeted with wide acclaim, and particularly pleased the new Pope, Urban VIII, to whom it had been dedicated. In Rome, in the previous decade, Barberini, the future Urban VIII, had come down on the side of Galileo and the Lincoln Academy. Galileo's dispute with Grassi permanently alienated many of the Jesuits who had previously been sympathetic to his ideas, and Galileo and his friends were convinced that these Jesuits were responsible for bringing about his later condemnation. The evidence for this is at best equivocal, however. Controversy over heliocentrism. In the Christian world prior to Galileo's conflict with the Church, the majority of educated people subscribed either to the Aristotelian geocentric view that the Earth was the center of the universe and that all heavenly bodies revolved around the Earth, or the Tychonic system that blended geocentrism with heliocentrism. Nevertheless, following the death of Copernicus and before Galileo, heliocentrism was relatively uncontroversial. Copernicus's work was used by Pope Gregory XIII to reform the calendar in 1582. Opposition to heliocentrism and Galileo's writings combined religious and scientific objections and were fueled by political events. Scientific opposition came from Tycho Brahe and others, and arose from the fact that, if heliocentrism were true, an annual stellar parallax should be observed, though none was. Copernicus had correctly postulated that parallax was negligible because the stars were so distant. However, Brahe had countered that, since stars appeared to have measurable size, if the stars were that distant, they would be gigantic, and in fact far larger than the Sun or any other celestial body. In Brahe's system, by contrast, the stars were a little more distant than Saturn, and the Sun and stars were comparable in size. Religious opposition to heliocentrism arose from biblical references such as Psalm 93, 1, 96, 10, and 1 Chronicles 16:30, which include texts stating that the world is firmly established, it cannot be moved. In the same manner, Psalm 104, 5 says, "The Lord set the earth on its foundations, it can never be moved." Further, Ecclesiastes 1, 5 states that, "And the sun rises and sets and returns to its place." Galileo defended heliocentrism based on his astronomical observations of 1609, Sidereus Nuncius 1610. In December 1613, the Grand Duchess Christina of Florence confronted one of Galileo's friends and followers, Benedetto Castelli, with biblical objections to the motion of the earth. According to Maurice Finocchiaro, this was done in a friendly and gracious manner, out of curiosity. Prompted by this incident, Galileo wrote a letter to Castelli in which he argued that heliocentrism was actually not contrary to biblical texts, and that the Bible was an authority on faith and morals, not on science. This letter was not published, but circulated widely. By 1615, Galileo's writings on heliocentrism had been submitted to the Roman Inquisition by Father Niccolò Lorini, who claimed that Galileo and his followers were attempting to reinterpret the Bible, which was seen as a violation of the Council of Trent and looked dangerously like Protestantism. Lorini specifically cited Galileo's letter to Castelli. Galileo went to Rome to defend himself and his Copernican and biblical ideas. At the start of 1616, Monsignor Francesco Ingoli initiated a debate with Galileo, sending him an essay disputing the Copernican system. Galileo later stated that he believed this essay to have been instrumental in the action against Copernicanism that followed. According to Maurice Finocchiaro, Ingoli had probably been commissioned by the Inquisition to write an expert opinion on the controversy, and the essay provided the chief direct basis for the Inquisition's actions. The essay focused on 18 physical and mathematical arguments against heliocentrism. It borrowed primarily from the arguments of Tycho Brahe, and it notedly mentioned Brahe's argument that heliocentrism required the stars to be much larger than the sun. Ingoli wrote that the great distance to the stars in the heliocentric theory clearly proves the fixed stars to be of such size, as they may surpass or equal the size of the orbit circle of the Earth itself. The essay also included 4 theological arguments, but Ingoli suggested Galileo focus on the physical and mathematical arguments, and he did not mention Galileo's biblical ideas. In February 1616, an inquisitorial commission declared heliocentrism to be foolish and absurd in philosophy, and formally heretical since it explicitly contradicts in many places the sense of Holy Scripture. The Inquisition found that the idea of the Earth's movement receives the same judgment in philosophy and, in regard to theological truth, it is at least erroneous in faith. The original document from the Inquisitorial Commission was made widely available in 2014. Pope Paul V instructed Cardinal Bellarmine to deliver this finding to Galileo, and to order him to abandon the opinion that heliocentrism was physically true. On the 26th of February, Galileo was called to Bellarmine's residence and ordered to abandon completely the opinion that the sun stands still at the center of the world and the earth moves, and henceforth not to hold, teach, or defend it in any way whatever, either orally or in writing. The decree of the Congregation of the Index banned Copernicus's De Revolutionibus and other heliocentric works until correction. Bellarmine's instructions did not prohibit Galileo from discussing heliocentrism as a mathematical and philosophic idea, so long as he did not advocate for its physical truth. For the next decade, Galileo stayed well away from the controversy. He revived his project of writing a book on the subject, encouraged by the election of Cardinal Maffeo Barberini as Pope Urban VIII in 1623. Barberini was a friend and admirer of Galileo, and had opposed the condemnation of Galileo in 1616. Galileo's resulting book, Dialogue Concerning the Two Chief World Systems, was published in 1632, with formal authorization from the Inquisition and papal permission. Earlier, Pope Urban VIII had personally asked Galileo to give arguments for and against heliocentrism in the book, and to be careful not to advocate heliocentrism. He made another request, that his own views on the matter be included in Galileo's book. Only the latter of those requests was fulfilled by Galileo. Whether unknowingly or deliberately, Simplicio, the defender of the Aristotelian geocentric view in dialogue concerning the two chief world systems, was often caught in his own errors and sometimes came across as a fool. Indeed, although Galileo states in the preface of his book that the character is named after a famous Aristotelian philosopher, Simplicius in Latin, Simplicio, in Italian, the name, Simplicio, in Italian also has the connotation of simpleton. This portrayal of Simplicio made dialogue concerning the two chief world systems appear as an advocacy book, an attack on Aristotelian geocentrism in defense of the Copernican theory. Unfortunately for his relationship with the Pope, Galileo put the words of Urban VIII into the mouth of Simplicio. Most historians agree Galileo did not act out of malice and felt blindsided by the reaction to his book. However, the Pope did not take the suspected public ridicule lightly, nor the Copernican advocacy. Galileo had alienated one of his biggest and most powerful supporters, the Pope, and was called to Rome to defend his writing in September 1632. He finally arrived in February 1633 and was brought before Inquisitor Vincenzo Maculeni to be charged. Throughout his trial, Galileo steadfastly maintained that since 1616 he had faithfully kept his promise not to hold any of the condemned opinions, and initially he denied even defending them. However, he was eventually persuaded to admit that, contrary to his true intention, a reader of his dialogue could well have obtained the impression that it was intended to be a defense of Copernicanism. In view of Galileo's rather implausible denial that he had ever held Copernican ideas after 1616 or ever intended to defend them in the dialogue, his final interrogation, in July 1633, concluded with his being threatened with torture if he did not tell the truth, but he maintained his denial despite the threat. The sentence of the Inquisition was delivered on the 22nd of June. It was in three essential parts. Galileo was found vehemently suspect of heresy, namely of having held the opinions that the sun lies motionless at the center of the universe, that the earth is not at its center and moves, and that one may hold and defend an opinion as probable after it has been declared contrary to Holy Scripture. He was required to abjure, curse and detest those opinions. He was sentenced to formal imprisonment at the pleasure of the Inquisition. On the following day this was commuted to house arrest, which he remained under for the rest of his life. According to popular legend, after recanting his theory that the earth moved around the sun, Galileo allegedly muttered the rebellious phrase "and yet it moves." A 1640s painting by the Spanish painter Bartolomé Esteban Murillo, or an artist of his school, in which the words were hidden until restoration work in 1911, depicts an imprisoned Galileo apparently gazing at the words, "E por si muove," written on the wall of his dungeon. The earliest known written account of the legend dates to a century after his death, but Stillman Drake writes, "There is no doubt now that the famous words were already attributed to Galileo before his death." After a period with the friendly Ascanio Piccolomini, the Archbishop of Siena, Galileo was allowed to return to his villa at Arcetri near Florence in 1634, where he spent the remainder of his life under house arrest. Galileo was ordered to read the 7 penitential psalms once a week for the next 3 years. However, his daughter Maria Celeste relieved him of the burden after securing ecclesiastical permission to take it upon herself. It was while Galileo was under house arrest that he dedicated his time to one of his finest works, Two New Sciences. Here he summarized work he had done some 40 years earlier, on the two sciences now called kinematics and strength of materials, published in Holland to avoid the censor. This book has received high praise from Albert Einstein. As a result of this work, Galileo is often called the father of modern physics. He went completely blind in 1638 and was suffering from a painful hernia and insomnia, so he was permitted to travel to Florence for medical advice. Dava Sobel argues that prior to Galileo's 1633 trial and judgment for heresy, Pope Urban VIII had become preoccupied with court intrigue and problems of state, and began to fear persecution or threats to his own life. In this context, Sobel argues that the problem of Galileo was presented to the Pope by court insiders and enemies of Galileo. Having been accused of weakness in defending the Church, Urban reacted against Galileo out of anger and fear. Death. Galileo continued to receive visitors until 1642, when, after suffering fever and heart palpitations, he died on the 8th of January 1642, aged 77. The Grand Duke of Tuscany, Ferdinando II, wished to bury him in the main body of the Basilica of Santa Croce, next to the tombs of his father and other ancestors, and to erect a marble mausoleum in his honor. These plans were dropped, however, after Pope Urban VIII and his nephew, Cardinal Francesco Barberini, protested, because Galileo had been condemned by the Catholic Church for vehement suspicion of heresy. He was instead buried in a small room next to the novices' chapel at the end of a corridor from the southern transept of the basilica to the sacristy. He was reburied in the main body of the basilica in 1737 after a monument had been erected there in his honor. During this move, 3 fingers and a tooth were removed from his remains. One of these fingers, the middle finger from Galileo's right hand, is currently on exhibition at the Museo Galileo in Florence, Italy. Scientific methods. Galileo made original contributions to the science of motion through an innovative combination of experiment and mathematics. More typical of science at the time were the qualitative studies of William Gilbert, on magnetism and electricity. Galileo's father, Vincenzo Galilei, a lutenist and music theorist, had performed experiments establishing perhaps the oldest known nonlinear relation in physics. For a stretched string, the pitch varies as the square root of the tension. These observations lay within the framework of the Pythagorean tradition of music, well known to instrument makers, which included the fact that subdividing a string by a whole number produces a harmonious scale. Thus, a limited amount of mathematics had long related music and physical science, and young Galileo could see his own father's observations expand on that tradition. Galileo was one of the first modern thinkers to clearly state that the laws of nature are mathematical. In the essay he wrote, "Philosophy is written in this grand book, the universe. It is written in the language of mathematics, and its characters are triangles, circles, and other geometric figures." Quote. His mathematical analyses are a further development of a tradition employed by late scholastic natural philosophers, which Galileo learned when he studied philosophy. His work marked another step towards the eventual separation of science from both philosophy and religion. A major development in human thought. He was often willing to change his views in accordance with observation. In order to perform his experiments, Galileo had to set up standards of length and time, so that measurements made on different days and in different laboratories could be compared in a reproducible fashion. This provided a reliable foundation on which to confirm mathematical laws using inductive reasoning. Galileo showed a modern appreciation for the proper relationship between mathematics, theoretical physics, and experimental physics. He understood the parabola, both in terms of conic sections and in terms of the ordinate varying as the square of the abscissa. Galilei further asserted that the parabola was the theoretically ideal trajectory of a uniformly accelerated projectile in the absence of air resistance or other disturbances. He conceded that there are limits to the validity of this theory, noting on theoretical grounds that a projectile trajectory of a size comparable to that of the Earth could not possibly be a parabola, but he nevertheless maintained that for distances up to the range of the artillery of his day, the deviation of a projectile's trajectory from a parabola would be only very slight. Astronomy. Based only on uncertain descriptions of the first practical telescope which Hans Lippershey tried to patent in the Netherlands in 1608, Galileo, in the following year, made a telescope with about 3x magnification. He later made improved versions with up to about 30x magnification. With a Galilean telescope, the observer could see magnified, upright images on the Earth. It was what is commonly known as a terrestrial telescope or a spyglass. He could also use it to observe the sky. For a time he was one of those who could construct telescopes good enough for that purpose. On the 25th of August 1609, he demonstrated one of his early telescopes, with a magnification of about 8 or 9, to Venetian lawmakers. His telescopes were also a profitable sideline for Galileo, who sold them to merchants who found them useful both at sea and as items of trade. He published his initial telescopic astronomical observations in March 1610 in a brief treatise entitled Sidereus Nuncius. Kepler's supernova. Tycho and others had observed the supernova of 1572. Ottavio Brenzoni's letter of the 15th of January 1605 to Galileo brought the 1572 supernova and the less bright nova of 1601 to Galileo's notice. Galileo observed and discussed Kepler's supernova in 1604. Since these new stars displayed no detectable diurnal parallax, Galileo concluded that they were distant stars, and therefore disproved the Aristotelian belief in the immutability of the heavens. Jupiter's moons. On the 7th of January 1610, Galileo observed with his telescope what he described at the time as 3 fixed stars, totally invisible by their smallness, all close to Jupiter, and lying on a straight line through it. Observations on subsequent nights showed that the positions of these stars, relative to Jupiter, were changing in a way that would have been inexplicable if they had really been fixed stars. On the 10th of January, Galileo noted that one of them had disappeared, an observation which he attributed to its being hidden behind Jupiter. Within a few days, he concluded that they were orbiting Jupiter. He had discovered 3 of Jupiter's 4 largest moons. He discovered the 4th on the 13th of January. Galileo named the group of 4 the Medicine Stars, in honor of his future patron, Cosimo II de' Medici, Grand Duke of Tuscany, and Cosimo's 3 brothers. Later astronomers, however, renamed them Galilean satellites in honor of their discoverer. These satellites are now called Io, Europa, Ganymede, and Callisto. His observations of the satellites of Jupiter caused a revolution in astronomy. A planet with smaller planets orbiting it did not conform to the principles of Aristotelian cosmology, which held that all heavenly bodies should circle the Earth, and many astronomers and philosophers initially refused to believe that Galileo could have discovered such a thing. His observations were confirmed by the observatory of Christopher Clavius, and he received a hero's welcome when he visited Rome in 1611. Galileo continued to observe the satellites over the next 18 months, and by mid-1611, he had obtained remarkably accurate estimates for their periods, a feat which Kepler had believed impossible. Venus, Saturn, and Neptune. From September 1610, Galileo observed that Venus exhibited a full set of phases similar to that of the Moon. The heliocentric model of the solar system developed by Nicolaus Copernicus predicted that all phases would be visible, since the orbit of Venus around the Sun would cause its illuminated hemisphere to face the Earth when it was on the opposite side of the Sun, and to face away from the Earth when it was on the Earth side of the Sun. On the other hand, in Ptolemy's geocentric model, it was impossible for any of the planets' orbits to intersect the spherical shell carrying the Sun. Traditionally, the orbit of Venus was placed entirely on the near side of the Sun, where it could exhibit only crescent and new phases. It was, however, also possible to place it entirely on the far side of the Sun, where it could exhibit only gibbous and full phases. After Galileo's telescopic observations of the crescent, gibbous and full phases of Venus, therefore, the Ptolemaic model became untenable. Thus, in the early 17th century, as a result of his discovery, the great majority of astronomers converted to one of the various geo-heliocentric planetary models, such as the Tychonic, Capellan and extended Capellan models, each either with or without a daily rotating Earth. These all had the virtue of explaining the phases of Venus without the vice of the refutation of full heliocentrism's prediction of stellar parallax. Galileo's discovery of the phases of Venus was thus arguably his most empirically practically influential contribution to the two-stage transition from full geocentrism to full heliocentrism via geoheliocentrism. Galileo observed the planet Saturn, and at first mistook its rings for planets, thinking it was a three-bodied system. When he observed the planet later, Saturn's rings were directly oriented at Earth, causing him to think that 2 of the bodies had disappeared. The rings reappeared when he observed the planet in 1616, further confusing him. Galileo also observed the planet Neptune in 1612. It appears in his notebooks as one of many unremarkable dim stars. He did not realize that it was a planet, but he did note its motion relative to the stars before losing track of it. Sunspots. Galileo made naked eye and telescopic studies of sunspots. Their existence raised another difficulty with the unchanging perfection of the heavens as posited in orthodox Aristotelian celestial physics. An apparent annual variation in their trajectories, observed by Francesco Sizzi and others in 1612-1613, also provided a powerful argument against both the Ptolemaic system and the geoheliocentric system of Tycho Brahe. A dispute over claimed priority in the discovery of sunspots, and in their interpretation, led Galileo to a long and bitter feud with the Jesuit Christoph Scheiner. In the middle was Mark Welser, to whom Scheiner had announced his discovery, and who asked Galileo for his opinion. In fact, there is little doubt that both of them were beaten by David Fabricius and his son Johannes. Moon. Prior to Galileo's construction of his version of a telescope, Thomas Harriot, an English mathematician and explorer, had already used what he dubbed a perspective tube to observe the moon. Reporting his observations, Harriot noted only strange spottedness in the waning of the crescent, but was ignorant to the cause. Galileo, due in part to his artistic training and the knowledge of chiaroscuro, had understood the patterns of light and shadow were in fact topographical markers. While not being the only one to observe the moon through a telescope, Galileo was the first to deduce the cause of the uneven waning as light occlusion from lunar mountains and craters. In his study he also made topographical charts, estimating the heights of the mountains. The moon was not what was long thought to have been a translucent and perfect sphere, as Aristotle claimed, and hardly the first planet, an eternal pearl to magnificently ascend into the heavenly empyrean, as put forth by Dante. Milky Way and stars. Galileo observed the Milky Way, previously believed to be nebulous, and found it to be a multitude of stars packed so densely that they appeared from Earth to be clouds. He located many other stars too distant to be visible with the naked eye. He observed the double star Mizar in Ursa Major in 1617. In the Starry Messenger, Galileo reported that stars appeared as mere blazes of light, essentially unaltered in appearance by the telescope, and contrasted them to planets, which the telescope revealed to be disks. But shortly thereafter, in his letters on sunspots, he reported that the telescope revealed the shapes of both stars and planets to be quite round. From that point forward, he continued to report that telescopes showed the roundness of stars, and that stars seen through the telescope measured a few seconds of arc in diameter. He also devised a method for measuring the apparent size of a star without a telescope. As described in his dialogue concerning the two chief world systems, his method was to hang a thin rope in his line of sight to the star and measure the maximum distance from which it would wholly obscure the star. From his measurements of this distance and of the width of the rope, he could calculate the angle subtended by the star at his viewing point. In his dialogue, he reported that he had found the apparent diameter of a star of first magnitude to be no more than 5 arcsecons, and that of one of sixth magnitude to be about 5/6 arcsecons. Like most astronomers of his day, Galileo did not recognize that the apparent sizes of stars that he measured were spurious, caused by diffraction and atmospheric distortion, seeing disk or airy disk, and did not represent the true sizes of stars. However, Galileo's values were much smaller than previous estimates of the apparent sizes of the brightest stars, such as those made by Tycho Brahe, and enabled Galileo to counter anti-Copernican arguments such as those made by Tycho that these stars would have to be absurdly large for their annual parallaxes to be undetectable. Other astronomers such as Simon Marius, Giovanni Battista Riccioli, and Martinus Hortensius made similar measurements of stars, and Marius and Riccioli concluded the smaller sizes were not small enough to answer Tycho's argument. Engineering. Galileo made a number of contributions to what is now known as engineering, as distinct from pure physics. Between 1595 and 1598, Galileo devised and improved a geometric and military compass suitable for use by gunners and surveyors. This expanded on earlier instruments designed by Niccolò Tartaglia and Guidobaldo del Monte. For gunners, it offered, in addition to a new and safer way of elevating cannons accurately, a way of quickly computing the charge of gunpowder for cannonballs of different sizes and materials. As a geometric instrument, it enabled the construction of any regular polygon, computation of the area of any polygon or circular sector, and a variety of other calculations. Under Galileo's direction, instrument maker Marcantonio Mazzoleni produced more than 100 of these compasses, which Galileo sold, along with an instruction manual he wrote, for 50 lire and offered a course of instruction in the use of the compasses for 120 lire. In about 1593, Galileo constructed a thermometer, using the expansion and contraction of air in a bulb to move water in an attached tube. In 1609, Galileo was, along with Englishman Thomas Harriot and others, among the first to use a refracting telescope as an instrument to observe stars, planets or moons. The name, telescope, was coined for Galileo's instrument by a Greek mathematician, Giovanni Demisiani, at a banquet held in 1611 by Prince Federico Sizzi to make Galileo a member of his Accademia dei Lincei. The name was derived from the Greek tele equals fa, and scopine equals to look or see. In 1610, he used a telescope at close range to magnify the parts of insects. By 1624, Galileo had used a compound microscope. He gave one of these instruments to Cardinal Zollin in May of that year for presentation to the Duke of Bavaria, and in September he sent another to Prince Sizzi. The Lincens played a role again in naming the microscope a year later when fellow Academy member Giovanni Faber coined the word for Galileo's invention from the Greek words micron meaning small, and scopine meaning to look at. The word was meant to be analogous with telescope. Illustrations of insects made using one of Galileo's microscopes, and published in 1625, appear to have been the first clear documentation of the use of a compound microscope. In 1612, having determined the orbital periods of Jupiter's satellites, Galileo proposed that with sufficiently accurate knowledge of their orbits, one could use their positions as a universal clock, and this would make possible the determination of longitude. He worked on this problem from time to time during the remainder of his life. But the practical problems were severe. The method was first successfully applied by Giovanni Domenico Cassini in 1681 and was later used extensively for large land surveys. This method, for example, was used to survey France, and later by Zebulon Pike of the Midwestern United States in 1806. For sea navigation, where delicate telescopic observations were more difficult, the longitude problem eventually required development of a practical portable marine chronometer, such as that of John Harrison. Late in his life, when totally blind, Galileo designed an escapement mechanism for a pendulum clock, called Galileo's escapement, although no clock using this was built until after the first fully operational pendulum clock was made by Christian Huygens in the 1650s. Physics. Galileo's theoretical and experimental work on the motions of bodies, along with the largely independent work of Kepler and René Descartes, was a precursor of the classical mechanics developed by Sir Isaac Newton. Galileo conducted several experiments with pendulums. It is popularly believed, thanks to the biography by Vincenzo Viviani, that these began by watching the swings of the bronze chandelier in the Cathedral of Pisa, using his pulse as a timer. Later experiments are described in his Two New Sciences. Galileo claimed that a simple pendulum is isochronous, i.e. that its swings always take the same amount of time, independently of the amplitude. In fact, this is only approximately true, as was discovered by Christian Huygens. Galileo also found that the square of the period varies directly with the length of the pendulum. Galileo's son, Vincenzo, sketched a clock based on his father's theories in 1642. The clock was never built and, because of the large swings required by its verge escapement, would have been a poor timekeeper. Galileo is lesser known for, yet still credited with, being one of the first to understand sound frequency. By scraping a chisel at different speeds, he linked the pitch of the sound produced to the spacing of the chisel's skips, a measure of frequency. In 1638, Galileo described an experimental method to measure the speed of light by arranging that two observers, each having lanterns equipped with shutters, observe each other's lanterns at some distance. The first observer opens the shutter of his lamp, and the second, upon seeing the light, immediately opens the shutter of his own lantern. The time between the first observer's opening his shutter and seeing the light from the second observer's lamp indicates the time it takes light to travel back and forth between the two observers. Galileo reported that when he tried this at a distance of less than a mile, he was unable to determine whether or not the light appeared instantaneously. Sometime between Galileo's death and 1667, the members of the Florentine Accademia del Cimento repeated the experiment over a distance of about a mile and obtained a similarly inconclusive result. We now know that the speed of light is far too fast to be measured by such methods. Galileo put forward the basic principle of relativity, that the laws of physics are the same in any system that is moving at a constant speed in a straight line, regardless of its particular speed or direction. Hence, there is no absolute motion or absolute rest. This principle provided the basic framework for Newton's laws of motion and is central to Einstein's special theory of relativity. Along a horizontal plane without friction, then we know, from what has been more fully explained in the preceding pages, that this particle will move along the same plane with a motion which is uniform and perpetual, provided the plane has no limits. This was incorporated into Newton's laws of motion. Mathematics. While Galileo's application of mathematics to experimental physics was innovative, his mathematical methods were the standard ones of the day, including dozens of examples of an inverse proportion square root method passed down from Fibonacci and Archimedes. The analysis and proofs relied heavily on the Eudoxian theory of proportion, as set forth in the fifth book of Euclid's Elements. This theory had become available only a century before, thanks to accurate translations by Tartaglia and others, but by the end of Galileo's life, it was being superseded by the algebraic methods of Descartes. The concept now named Galileo's paradox was not original with him. His proposed solution, that infinite numbers cannot be compared, is no longer considered useful. Writings. Galileo's early works describing scientific instruments include the 1586 tract entitled The Little Balance, La Bilancetta, describing an accurate balance to weigh objects in air or water, and the 1606 printed manual La Operazione del Compasso Geometrico et Militare on the operation of a geometrical and military compass. His early works in dynamics, the science of motion and mechanics were his 1590 Piston de Motu, on motion, and his circa 1600 Paduan La Mécanique, mechanics. The former was based on Aristotelian Archimedean fluid dynamics and held that the speed of gravitational fall in a fluid medium was proportional to the excess of a body's specific weight over that of the medium, whereby in a vacuum, bodies would fall with speeds in proportion to their specific weights. It also subscribed to the Philoponnan impetus dynamics, in which impetus is self-dissipating and free fall in a vacuum would have an essential terminal speed according to specific weight after an initial period of acceleration. Galileo's 1610 The Starry Messenger, Sidereus Nuncius, was the first scientific treatise to be published based on observations made through a telescope. It reported his discoveries of the Galilean moons, the roughness of the moon's surface, the existence of a large number of stars invisible to the naked eye, particularly those responsible for the appearance of the Milky Way. Differences between the appearances of the planets and those of the fixed stars, the former appearing as small disks, while the latter appeared as magnified points of light. Galileo published a description of sunspots in 1613 entitled Letters on Sunspots, suggesting the sun and heavens are corruptible. The Letters on Sunspots also reported his 1610 telescopic observations of the full set of phases of Venus, and his discovery of the puzzling appendages of Saturn and their even more puzzling subsequent disappearance. In 1615, Galileo prepared a manuscript known as the Letter to the Grand Duchess Christina, which was not published in printed form until 1636. This letter was a revised version of the Letter to Castelli, which was denounced by the Inquisition as an incursion upon theology by advocating Copernicanism both as physically true and as consistent with Scripture. In 1616, after the order by the Inquisition for Galileo not to hold or defend the Copernican position, Galileo wrote the Discourse on the Tides, Discorso sul flusso e il riflesso del mare, based on the Copernican Earth, in the form of a private letter to Cardinal Orsini in 1619. Mario Guiducci, a pupil of Galileo's, published a lecture written largely by Galileo under the title Discourse on the Comets, Discorso del Comet, arguing against the Jesuit interpretation of comets. In 1623, Galileo published the Essay, Il Saggiatore, which attacked theories based on Aristotle's authority and promoted experimentation and the mathematical formulation of scientific ideas. The book was highly successful and even found support among the higher echelons of the Christian Church. Following the success of the essay, Galileo published the dialogue concerning the two chief world systems, Dialogo sopra I due massimi sistemi del mondo, in 1632. Despite taking care to adhere to the Inquisition's 1616 instructions, the claims in the book favoring Copernican theory and a non-geocentric model of the solar system led to Galileo being tried and banned on publication. Despite the publication ban, Galileo published his discourses and mathematical demonstrations relating to two new sciences, Discorsi e dimostrazioni matematiche, intorno a due nuove scienze, in 1638 in Holland, outside the jurisdiction of the Inquisition. Published written works. Galileo's main written works are as follows. The Little Balance, 1586, in Italian, La Bilancetta. On Motion, circa 1590, in Latin, De Motu Antiquiora. Mechanics, circa 1600, in Italian, La Meccaniche. The Operations of Geometrical and Military Compass, 1606, in Italian, Le Operazioni del Compasso Geometrico et Militare. The Starry Messenger, 1610, in Latin, Sidereus Nuncius. Discourse on Floating Bodies, 1612, in Italian, Discorso intorno al cosce stanno in sull'acqua, o che in quella si muovono, Discourse on Bodies that stay atop water, or move in it. History and Demonstration concerning Sunspots, 1613, in Italian, Storia e dimostrazioni intorno al machisolari, work based on the three letters on sunspots, ter letter sul machisolari, 1612. Letter to the Grand Duchess Christina, 1615, published in 1636. Discourse on the Tides, 1616, in Italian, Discorso del flusso e riflusso del mare, Discourse on the Comets, 1619, in Italian, Discorso del Comet, the Assayer, 1623, in Italian, Il Saggiatore. Dialogue concerning the two chief world systems, 1632, in Italian, Dialogo sopra I due massimi sistemi del mondo. Discourses and mathematical demonstrations relating to two new sciences, 1638, in Italian, Discorsi e dimostrazioni matematiche, intorno a due nuove scienze. Legacy. Later church reassessments. The Galileo affair was largely forgotten after Galileo's death, and the controversy subsided. The Inquisition's ban on reprinting Galileo's works was lifted in 1718 when permission was granted to publish an edition of his works, excluding the condemned dialogue, in Florence. In 1741 Pope Benedict XIV authorized the publication of an edition of Galileo's complete scientific works which included a mildly censored version of the dialogue. In 1758 the general prohibition against works advocating heliocentrism was removed from the index of prohibited books, although the specific ban on uncensored versions of the dialogue and Copernicus's De Revolutionibus remained. All traces of official opposition to heliocentrism by the Church disappeared in 1835 when these works were finally dropped from the index. Interest in the Galileo affair was revived in the early 19th century, when Protestant polemicists used it, and other events such as the Spanish Inquisition and the Flat Earth myth, to attack Roman Catholicism. Interest in it has waxed and waned ever since. In 1939 Pope Pius XII, in his first speech to the Pontifical Academy of Sciences, within a few months of his election to the papacy, described Galileo as being among the most audacious heroes of research. Not afraid of the stumbling blocks and the risks on the way, nor fearful of the funereal monuments. His close advisor of 40 years, Professor Robert Lieber, wrote, Pius XII was very careful not to close any doors to science prematurely. He was energetic on this point and regretted that in the case of Galileo. On the 15th of February 1990, in a speech delivered at the Sapienza University of Rome, Cardinal Ratzinger, later to become Pope Benedict XVI, cited some current views on the Galileo affair as forming what he called a symptomatic case that permits us to see how deep the self-doubt of the modern age of science and technology goes today. Some of the views he cited were those of the philosopher Paul Feyerabend, whom he quoted as saying, "The Church at the time of Galileo kept much more closely to reason than did Galileo himself, and she took into consideration the ethical and social consequences of Galileo's teaching too." Her verdict against Galileo was rational and just, and the revision of this verdict can be justified only on the grounds of what is politically opportune. The cardinal did not clearly indicate whether he agreed or disagreed with Feyerabend's assertions. He did, however, say, it would be foolish to construct an impulsive apologetic on the basis of such views. On the 31st of October 1992, Pope John Paul II expressed regret for how the Galileo affair was handled, and issued a declaration acknowledging the errors committed by the Catholic Church tribunal that judged the scientific positions of Galileo Galilei, as the result of a study conducted by the Pontifical Council for Culture. In March 2008, the head of the Pontifical Academy of Sciences, Nicola Cabibbo, announced a plan to honor Galileo by erecting a statue of him inside the Vatican walls. In December of the same year, during events to mark the 400th anniversary of Galileo's earliest telescopic observations, Pope Benedict XVI praised his contributions to astronomy. A month later, however, the head of the Pontifical Council for Culture, Gianfranco Ravasi, revealed that the plan to erect a statue of Galileo in the grounds of the Vatican had been suspended. Impact on modern science. According to Stephen Hawking, Galileo probably bears more of the responsibility for the birth of modern science than anybody else, and Albert Einstein called him the father of modern science. Galileo's astronomical discoveries and investigations into the Copernican theory have led to a lasting legacy, which includes the categorization of the 4 large moons of Jupiter discovered by Galileo, Io, Europa, Ganymede and Callisto, as the Galilean moons. Other scientific endeavors and principles are named after Galileo, including the Galileo spacecraft, the first spacecraft to enter orbit around Jupiter, the proposed Galileo Global Satellite Navigation System, the transformation between inertial systems in classical mechanics denoted Galilean transformation, and the GAL, sometimes known as the Galileo, which is a non-SI unit of acceleration. Partly because 2009 was the 4th centenary of Galileo's first recorded astronomical observations with the telescope, the United Nations scheduled it to be the International Year of Astronomy. A global scheme was laid out by the International Astronomical Union, IAU, also endorsed by UNESCO, the UN body responsible for educational, scientific and cultural matters. The International Year of Astronomy 2009 was intended to be a global celebration of astronomy and its contributions to society and culture, stimulating worldwide interest not only in astronomy but science in general, with a particular slant towards young people. Asteroid 697 Galileo is named in his honor. In artistic and popular media, Galileo is mentioned several times in the opera section of the Queen's song, Bohemian Rhapsody. He features prominently in the song, Galileo, performed by the Indigo Girls and Amy Grant's Galileo on her Heart in Motion album. 20th century plays have been written on Galileo's life, including Life of Galileo, 1943, by the German playwright Bertolt Brecht, with a film adaptation, 1975, of it, and Lamp at Midnight, 1947, by Barry Stavis, as well as the 2008 play, Galileo Galilei. Kim Stanley Robinson wrote a science fiction novel entitled Galileo's Dream, 2009, in which Galileo is brought into the future to help resolve a crisis of scientific philosophy. The story moves back and forth between Galileo's own time and a hypothetical distant future, and contains a great deal of biographical information. Galileo Galilei was recently selected as a main motif for a high-value collector's coin, the €25 International Year of Astronomy commemorative coin, minted in 2009. This coin also commemorates the 400th anniversary of the invention of Galileo's telescope. The obverse shows a portion of his portrait and his telescope. The background shows one of his first drawings of the surface of the moon. In the silver ring, other telescopes are depicted. The Isaac Newton telescope, the observatory in Cranesminster Abbey, a modern telescope, a radio telescope and a space telescope. In 2009, the Galileoscope was also released. This is a mass-produced, low-cost educational 2-inch, 51mm, telescope with relatively high quality. Timeline. 1543 Nicolaus Copernicus publishes De Revolutionibus Orbium Coelestium as an alternative world system to the Ptolemy's geocentric model, causing subsequent questions to be raised about Aristotelian physics following Copernicus' death. 1563 Parents Vincenzo Galilei and Giulia Amannati marry. 1564 Birth in Pisa, Italy. 1570 Thomas Digges publishes Pantometria describing a telescope built between 1540–1559 by his father Leonard Digges. 1573 Tycho Brahe publishes De Nova Stella, on the new star, refuting Aristotelian belief in immutable celestial spheres and an eternal, unchanging, more perfect heavenly realm of celestial ether above the moon. 1576 Giuseppe Maletti, Galileo's predecessor in the mathematics chair at Padua, reports falling bodies of the same shape fall at the same speed, regardless of material. 1581 His father, Vincenzo Galilei, publishes Dialogo della musica antica et moderna formulating musical theories. 1581 Enrolls as medical student at University of Pisa. 1582 Attends mathematics lecture by Ostilio Ricci and decides to study math and science. 1585 Leaves University of Pisa without degree and works as tutor. 1586 Invents hydrostatic balance, wrote La Balancetta, the little balance. 1586 Simon Stevan publishes results for dropping lead weights from 10 meters. 1588 Tycho Brahe publishes work on comets containing a description of the Tychonic system of the world. 1589 Appointed to mathematics chair, University of Pisa. 1590 Partially completes the Motu, on motion, which is never published. 1591 Death of his father, Vincenzo Galilei. 1592 Appointed Professor of Mathematics at University of Padua, remains 18 years. 1593 Invents early thermometer that unfortunately depended on both temperature and pressure. 1595 Invents improved ballistics calculation, geometric and military compass, which he later improves for surveying and general calculations, and earns income from tutoring on its use. 1597 Letter to Kepler indicates his belief in the Copernican system. 1600 First child, Virginia, is born. 1600 Le Mécanique, mechanics. 1600 William Gilbert publishes on the magnet and magnetic bodies, and on that great magnet the earth, with arguments supporting the Copernican system. 1600 Roman Inquisition finds Giordano Bruno, Copernican system supporter, guilty of heresy for opinions on pantheism and the eternal plurality of worlds, and for denial of the Trinity, divinity of Christ, virginity of Mary, and transubstantiation, burned at the stake by civil authorities. 1601 Daughter Livia is born. 1604 Measures supernova position indicating no parallax for the new star. 1605 Sued by brothers-in-law for non-payment of sisters' dowries. 1606 Son Vincenzo born. 1606 Publishes manual for his calculating compass. 1607 Rotilio Orlandini attempts to assassinate Galileo's friend, Friar Paolo Serpi. 1608 Hans Lippershey invents a refracting telescope. 1609 Independently invents and improves telescopes based on description of invention by Hans Lippershey. 1609 Kepler publishes Astronomia Nova containing his first two laws, and for the first time demonstrates the Copernican model is more accurate than the Ptolemaic for uses such as navigation and prediction. 1609 Thomas Harriot sketches the moon from telescopic observations made 4 months before Galileo's. 1610 publishes Sidereus Nuncius, Starry Messenger, views our moon's mountains and craters and brightest 4 of Jupiter's moons. 1610 Martin Hawkey publishes Brevissima Peregrinatio contra Nuncium Sidereum, opposing Galileo. 1610 Kepler requests one of Galileo's telescopes or lenses, but Galileo replies he is too busy to build one and has no extras. 1610 Lifetime appointment to mathematics position at University of Padua, and is mathematician and philosopher for Cosimo II, Grand Duke of Tuscany. 1611 Discovers phases of Venus, granted audience with Pope, made member of Lincoln Academy. 1611 Awarded an honorary degree by the Jesuit College in Rome. 1611 David Fabricius publishes narration on spots observed on the Sun and their apparent rotation with the Sun prior to Christoph Scheiner and Galileo's published works on the subject. 1612 Proposed Jupiter's moons could be used as a universal clock for possible determination of longitude. 1612 or 1613 Francesco Sizzi discovers annual variations in sunspots motions. 1613 Letters on sunspots. 1613 Letter to Benedetto Castelli discussing the rotation of the Sun and Galileo's support of the Copernican system. Using biblical inerrancy as a basis, Galileo writes that Joshua's command for the Sun to stand still in Joshua 10:13 proves the impossibility of the Aristotelian and Ptolemaic world system, and on the other hand agrees very well with the Copernican one. He went on to write that, the Sun gives not only light, as it obviously does, but also motion to all the planets that revolve around it, by its rotation. 1615 Letter to Grand Duchess Christina, not published until 1636. 1616 Officially warned by the Church not to hold or defend the Copernican system. 1616 The Catholic Church places De Revolutionibus Orbium Coelestium on the list of prohibited books, pending correction. 1616 Private letter discourse on the tides. 1617 moves into Bellosguardo, west of Florence, near his daughter's convent, observes double star Mizar in Ursa Major. 1619 Kepler publishes Harmonices Mundi, which introduces his third law. 1619 Discourse on the comets. 1623 Maffeo Barberini becomes Pope Urban VIII. 1623 publishes the Assayer. 1624 visits Pope who praises and honors him, leaving with assumed permission to publish work on the Copernican vs. Ptolemaic systems. Used a compound microscope. 1625 Illustrations of insects made using one of Galileo's microscopes published. 1630 Completes dialogue concerning the two chief world systems and subsequently receives approval of church censor. 1632 Publishes dialogue concerning the two chief world systems. 1633 Sentenced by the Inquisition to imprisonment, commuted to house arrest, for vehement suspicion of heresy in violating the 1616 injunction. 1633 Catholic Church places dialogue concerning the two chief world systems on the list of prohibited books. 1638 Publishes dialogues concerning two new sciences. 1642 Death in Arcetri, Italy. 1668 Isaac Newton builds his reflecting telescope. 1687 Isaac Newton publishes Philosophiae Naturalis Principia Mathematica, deriving Kepler's laws from the universal law of gravitation and the laws of motion. 2016 The American Juno spacecraft, carrying a plaque and a Lego minifigure dedicated at Galileo, arrives at Jupiter's orbit.
Thank you.